Okay, hello friends. Now today we are going to see the measurement of the dryness fraction by experimental methods. So see, measuring dryness fraction is also important point because the dryness fraction is giving you one important property and that you should measure with the experimentations. So today we are going to see it. So what is that? Let us see. The first is that what is meant by the dryness fraction. So dryness fraction is defined as mass of dry vapor in the given steam divided by total mass of given steam. So this we have seen for last lectures that dryness fraction is nothing but the if we are having some sample of steam or the steam generated by the boiler, then in that steam what amount of steam is there and what amount of water moisture content is there. Based on that, the dryness fraction is defined. So mass of dry vapor in a given steam divided by total mass of given steam is called as a dryness fraction, and that is X. Now we have to measure it, and this is measured with the instrument called calorimeters. Okay, calorimeters. See, I think you have seen one calorimeter. We have seen calorimeter, that is bomb calorimeter. So what is mean by the calorimeters? The meaning of calorimeter is the instrument which measures the calories is called as a calorimeter. So in case of bomb calorimeter or gas calorimeters, the instrument is measuring the calories of the fuel in terms of the calorific values. So that's why those are called as a calorific calorimeters. But in this case, we are going to measure the dryness fraction. So how you can relate the dryness fraction with the calories? See, the dryness fraction is an important property which decides that how much heat content is there by the steam, and that is nothing but the calories of the steam. So if you find out the dryness fraction of the steam, it means that you are finding out the calories of the steam. Okay, because you are knowing that formula HB is equal to HF plus XHFG. So if X is less or more, depending on that, the H value will change, that is calories of the steam will change. So the dryness fraction is a responsible factor for the calories in the steam. So that's why the instrument which is measuring the calories of the steam is called as a calorimeter. Okay, so there are different types of the calorimeters. Let us see that. So there are different types of calorimeters. Generally the four calorimeters are there in our syllabus. So we will see the first one is bucket or barrel calorimeter. Then second is there, that is separating type calorimeter. Third is there, that is throttling type calorimeter. And fourth is there, that combined separating and throttling calorimeter. So these are the four types of the calorimeter. See, each calorimeter is having its own advantages, drawbacks, accuracy wise, all are different. And we have to select what applications we are having or why, how much accuracy we required. Based on that, the calorimeters are selected. So let us go to the first type of the calorimeter, that is bucket or barrel type calorimeter. See, bucket or barrel type calorimeter is a simple calorimeter. It is having a just barrel. Okay, so you may know that barrel म्हणजे काय तुम्हाला माहिती आहे सगळ्यांना. So it is a tank, or you can say that huge reservoir we can have, not huge but a reservoir of known quantity. So you can say that in this case also we will have a barrel or tank of water in which the water is there, that water tank is there. Now this water tank is completely insulated. You can see that this is insulated. Okay, and in this water tank you will have the cold water. The mass of that cold water is m2. Mass of that water is m2, and initial temperature is T1. Okay, initial temperature of that water, whatever we are considering in this barrel, is T1. Mass of that calorimeter water is m2. While see, whatever the instrument you are taking, or you can say that that barrel is taking, that may be the copper barrel. Then if you take the copper barrel, then the mass of that barrel is m1 and the temperature is same as that of the water. We have to consider that the temperature of barrel and temperature of water will be same. And it will be same if it is having the equilibrium. Means if you are having the steady state conditions, then that both temperatures of barrel and temperatures of water will be same. So that M1 is the mass of barrel and T1 is the temperature of that barrel. While M2 is the mass of cold water and T1 is the temperature of the water. Now in this water, you will insert a pipe which is giving the steam, or you can say that which is taking the steam from the main steam pipe. So you can see here that there is a main steam pipe. Is it visible to all of you? Is it visible to all of you or not? If you are not visible, it is not visible, then tell me, because uh, I should not go blankly. Is it visible to all of you? Okay, so you can see that at the upper part, there is a pipe through which the wet steam is coming out of the boiler. Okay, so from the boiler it is coming out. That is steam coming out of the boiler, and out of that steam, some steam you will take for measuring the drain inspection. See, I want to measure the drain inspection of the steam which is given by the boiler. So some part of that I will take in the barrel, and that pipe is there. So you want to close and open the supply, that's why there is a wall. You can measure the pressure of that steam also, and one thermometer is inserted inside that barrel water, so that you can measure the temperature of the water. See, we can measure the temperature of the water, and as this barrel is completely insulated, then what it means? It means that we are not having any sort of heat losses. Heat is not going outside the barrel. So that is our consideration. That is our consideration. So this is the construction of barrel type or bucket type calorimeter. So just I have sorted out some points which will be helpful for all of you. Instead of remembering this, I will share this PPT with you also, so you can read it. That it consists a copper vessel which contains the known quantity of cold water, that is we are saying M2. Then the copper vessel is insulated from the surrounding so as to prevent any heat transfer from the system or to the system, and the top of the vessel is also covered with some detachable insulating medium, so that the heat loss is not there. And you will have one thermometer which is inserted inside that water to record the temperature. So this is all about the construction of the barrel type calorimeter. So what you will do, whatever the steam is coming from the boiler, that you will mix with this water. So when you will mix the steam with this water, that steam will gets condensed. That steam will becomes water, and that will gets cooled. So you can say that the mixing of steam will takes place. Mixing of steam will takes place in this case. Okay. So now in this case, what is going to happen? A steam condenses and the mass and temperature of water increases. So you can say that, suppose this is the first diagram which is showing you when you are mixing the steam, and due to that mixing process, the bubbles will be generated, and that bubbles will be lapse in the water, because you will have the huge water, and that will give the heat to the water as well as the barrel. Its temperature will increase, and in final case, after mixing of the same sample, the temperature will increase, and that is T2. We can say T2. So initial conditions are T1, final conditions are T2. The mass of barrel will remain same, but mass of warm water will increase. Mass of water will increase, and combinedly the total mass is going to increase. So we will have the weighing machine. With that weighing machines, you can measure the initial mass of the water and the initial mass of the barrel, and you can measure it after mixing of the steam, that is final mass of barrel and final mass of water. In this case, mass of barrel, or that is vessel, is not going to change, but the mass of water will increase. Mass of water will increase. So that is M3. M1 will not change, but temperature is going to increase, so that will becomes T2. So this is all about the procedures that you will have. Okay, so simple procedure is there. Now in this case, what is going to happen, see here, that I want to show you that whatever the diagrams we are plotting. Okay, so see, let us consider that this is our diagram. So what is going to happen now? We are having the water, we are having the water whose condition is A point. The condition of water which is available is at A point. Is it okay? A point. Okay, and while we are having the steam which is coming inside the barrel is B point. So the A point is showing you the water and B point is showing you the steam which is coming from the boiler. Now if you mix A and B, means A water and B steam, then what will happen? The point will comes in between A to B. The point will comes between A to B. Now it is not going to happen that all water is converted into the steam, but that steam will be converted into the water, so that will between A to F. A to F. So you can say that the final conditions of this system will be in between A and F. You can say that the final conditions of this system will be from A to F. So that you can consider as a 2 point. Okay, we can consider that is as a 2 point. So you will have the 2 point in the subcooled region. A point is in the subcooled region. That is 1 point is in the subcooled region. 2 point is also in the subcooled region. While the B point is in the wet steam region. Okay, so that is steam point that is in the wet region. A is initial conditions of the water, and the 2 point is which is in between A and F is again the final condition of the mixture which is in the liquid region. So that is you should understand. Now what formulas we are going to use it for this, that we have to discuss now. So what formulas we are going to use, that we have to discuss. So see, in this case, the simple energy balance equation is used. In this case, we are going to use the simple energy balance equation. What is that energy balance equation? Energy balance equation, we are going to say that the whatever the amount of the steam given by the steam, whatever the amount of the heat, not steam, whatever the amount of the heat given by the steam is equal to amount of the heat received by barrel, that is vessel, or the water. Okay, so that is the energy balance equation we will have. See, in this case, energy is given by the steam and that is received by water and vessel. So steam received by water and vessel is equal to the energy given by the steam. So you can write here that Q lost by steam, we can find out it like this: the mass of steam into Q water plus Q water. See, there are two stages, and Q lost by steam is equal to that CPW TS minus T2. See, we have seen that T2 point is somewhat below TS. So that heat plus X into HFG. HFG is for what? That is for the B point. Are you getting this point? How I am taking this? And then next, heat gained by the water in calorimeter, we can write mass of calorimeter, that is vessel, into Cp of vessel T2 minus T1 plus mass of water in the what we can say barrel into Cp of the water into T2 minus T1. So likewise you will have the two equations, and you can equate these two equations because there is no heat loss from the system to the surrounding. So if you equate this, then all the things are known to you. You have to find out that is Q lost by steam is equal to Q gained by the water, and you can find out the X value in this case. So likewise you can find out the dryness fraction by using bucket or barrel calorimeter. Bucket or barrel calorimeter. Okay. Now see what are the difficulties in this case. So here you can see that there are different parameters. I have explained what I have taken here. You can read it. You can read it. And what are the limitations for this? See, limitations for this is that value of x is not exactly correct, because see, there is we are considering that there is no heat losses, but still the heat loss may takes place from the insulation. So due to that, we will have the some errors, because whatever the equations we have considered, that is heat loss by steam is equal to heat loss by heat gain by water, it may not be correct. So that's why there is incorrect value of x may occur. That is first limitation. And second limitation is there, that suppose we are having very high pressure. Suppose steam is having with high pressure, then it will, what will happen? It will not condense. Okay, it will not condense, and it will escape from the water. So due to that, we can say that whatever the equation we are using, that is not going to be uh, correct. It may goes wrong. In this case, whatever the equation we are considering, that may not be correct, because it will not condense, but it is going as a remaining as a steam only. If the pressure, very high pressure you are going to use, see in this case, suppose I am sending the very high pressure steam, then that will not condense, but it will comes at the upper part of the vessel, and that may cause the error when the pressure will be higher. So when the pressure is higher, then this problem will occur, and we can't measure the dryness fraction with the barrel type calorimeter. So barrel type calorimeters are used for rough calculations where the dryness fraction is very low, and we want to measure the dryness fraction. Then in that case, the barrel calorimeters are useful. But if you are having very high pressures, high temperatures, steam, then it is not possible to use the barrel calorimeter. So this is the limitation of barrel calorimeter.